Depth First Search Algorithm, or more informally DFS. This algorithm is one of the most fundamental algorithms in graph theory and many of the ideas. In this video, we'll carry more advanced graph algorithms for that reason. In this video, we're going to spend some extra time building intuition for the ideas behind this algorithm. Here's what you can expect to get out in this video. We will first introduce what is depth first search. Second, the implementation of how depth search algorithm works in Java program. Last is the simulation. Let's get started.
Good day, sir, and to our viewers. I am Princess Alessandra Otaza, and I am here to give you a little understanding and knowledge about our topic, which will be deepened by Mr. Brix Marande's code and Mr. Jomari Oronan's simulation. Our topic is Deep First Search Algorithm. What is Deep First Search Algorithm anyway? Well, Deep First Search Algorithm, or DFS, is the most fundamental search algorithm used to explore nodes and edges of a graph. The good thing about this algorithm is it is easy to code and it runs with a time complexity of O, V plus E, which is often used as a building block in other algorithms. By itself, the DFS isn't all that useful, but when augmented to perform other tasks such as count connected components, determine connectivity, or find bridges or articulation points, then DFS really shines. So, Deep First Search, or DFS, is a graph traversal algorithm that explores as far as possible along each branch before backtracking. It's a common algorithm used in various applications, such as finding connected components in a graph, topological sorting, and solving puzzles like mazes. DFS has various applications, and it's a fundamental algorithm in a graph theory. It's worth noting that DFS does not necessarily find the shortest path in weighted graphs and is better suited for exploring all possibilities in an unweighted or equally weighted graph. Deep First Search holds significant importance across multiple domains in computer science and graph theory. As a fundamental algorithm, DFS plays a crucial role in graph traversal, enabling the identification of connected components in undirected graphs and facilitating the topological sorting of directed acyclic graphs for applications in scheduling and tasks planning. Its ability to find paths through mazes and solve spatial problems, such as the N-Quince problem, highlights its practicality and algorithm design. DFS is integral to cycle detection in graphs, aiding in application like deadlock detection in operating systems. Additionally, DFS is employed in compiler design during syntax analysis, constructing abstract syntax trees, and network analysis. DFS helps determine connectivity and identifies critical points and edges. Its use extends to game development for tree traversal in game trees, and it finds applications in data mining and machine learning for pattern matching. Furthermore, DFS is utilized in bioinformatics for genetic sequencing and brain connectivity analysis in neuroscience. Overall, DFS versatility makes it a powerful tool for systematically exploring graphs and solving diverse problems in various fields. Let's now direct our interest to Mr. Brix Marande's code.
Thank you, Ms. Otaza, for that wonderful discussion about the background of the deeper search algorithm. And now I am here to discuss the short implementation of how deeper search algorithm works in a Java program. So here I've created a simple implementation on how the deeper search works. So here I've already coded a sample to save time. So first let us discuss the parts of this code. So first group is the graph class that is used to represent the graph using an adjacency list. So here is the adjacency list, and we have the for loop and the initial capacity of the vertices, and then the add edge method that adds an edge between two vertices. So next is the DFS method. Here it is. So the first search method performs DFS traversal starting from a given vertex. So later we have the example. So here is our main method. So there is our main method. So now we've inserted the vertices, 6 initial vertices, which is 6, and in the main method, a sample graph is created with 6 vertices and edges. So the DFS traversal is started from vertex 0 using DFS algorithm. So I have a note here to, un- to further discuss. So you have created a here we've to start the vertex is always 0. So here we have to sample in. So let's analyze this. So the 0 push neighbors 1 and 2 into the stack, and then pop 2 and visit 2 push neighbors 4 and 5 here, 4 and 5 into the stack. So pop 5 and visit 5. So after that, pop 4 and visit 4. And then after we visited in the right side, on the right side, now we've pop number 1. So visit 1. The stack is now empty, and the DFS traversal is now complete. So here is the final result would be this. So we run this file, and now with 0 2 4 1. That's it for the short implementation on the DFS traversal in Java. So for more info about the DFS traversal, here's Mr. Oronan to discuss a short simulation about the DFS traversal. Take it away, Mr. Oronan.
Thank you, Mr. Marande. So let's look at an example as the name suggests. A depth first search plunges depth first into a graph with that regard for which edge it select next until you cannot go any further, at which point it backtracks and continues its exploration. So a depth first search has to start on a node, and I'm going to start our depth first search on node 0. And now we arbitrarily pick a node to go to. Some from node 0, we're going to go to node 9. Then from node 9, we only have one choice, which is to node 8. At node 8, arbitrarily pick an edge, so we're going to go outwards to node 7. Node 7, we have plenty of edges to choose from. So let's go to node 10. Node 10 to node 11, and 11 to 7. So we don't want to revisit already visited node or nodes that are currently being visited. So we have to backtrack to indicate backtracking. I'm going to label edges and node as gray. So backtrack all the way back to node 7. So we're not finished exploring node 7 because there are still edges to be picked. So I'm going to go to node 3. In node 3, I'm going to node 2. Node 2 is a dead end. So we backtrack, then go to node 4. Node 4 is also a dead end. So backtrack from node 4 back to node 3, then pick node 3 last edge to go to node 5, 5 to 6, 6 to 7, can't go to 7 because we're visiting 7 currently, so backtrack all the way back to node 8. From node 8, we still need to visit its last edge, which goes to node 1, back to node 0. We can't go to node 0 because we're currently exploring it. Then backtrack all the way to 0, which completes our first search traversal of this graph.